All right, so we're looking at the applications of the dot product here. All right, so one of the things that you can do with the dot product is you can find the angle between two vectors, okay? And the reason that is A dot B is equal to A magnitude B magnitude cosine theta. And as you can kind of see here, cosine theta is the angle between the two vectors. So if I algebraically isolate for it, I can see that I end up with cosine theta equals A dot B over the magnitude of each. All right. Oh, shoot. Okay. And that is going to be our angle between them. You got to take the cosine inverse. And so in the end, it's equal to the angle between the two vectors would be cosine inverse of A dot B over AB, each magnitudes. Okay. And so just a quick example of that. Let's say I ended up having two vectors, angles, vectors A and B. Let's say there are these ones up here, 2, 4, and 3, -1. So A is 2, 4. B is 3, -1. If I want to find the angle between these two guys, I simply just employ this new formula. So it's the cosine inverse of A dot B, which would be 3, actually, it would be 2 times 3 plus 4 times -1 over the magnitude of A, which is 2 squared plus 4 square rooted, times the magnitude of B, which would be 3 squared plus -1 squared, also rooted. And this is the angle between the two vectors. Okay, we already know that the dot product is just going to be is going to be 2. So it's cosine inverse of 2 over root of 20. Is that 20 times 10, root of 200. All right. And so that's what we've got there. The root of 200 is actually interesting. It's equal to 10 root 2. Anyway, let me figure out what this angle is. And so it's not that I know the cosine inverse of 2 over 2 root 2, 10 root 2. And so let me go ahead and calculate that. So it's going to be the cosine inverse of 1 divided by 5 root, oops, where to go? Root 2. If I type that in, right? Cosine inverse. It's going to be about 73 degrees. So basically, what we up here when I when I drew these angles, actually I drew these up here. This is A and B, so it turns out this is around 73 degrees in there. Okay, because this is angle. Oh, sorry, these are the two vectors from before. Okay. Another application for the dot product is work. Okay, and this is a physics concept. Work is force times displacement, okay, which is equal to the force magnitude times the change in position, or the displacement magnitude, times the cosine of the angle. Those of you in physics class would find this as a familiar formula, right? You can see that this is actually a dot product formula, right? So I may have mentioned it in physics class. We don't use it in Cartesian form, but we tend to use it in physics class in the geometric form, because most of our angles in physics are in geometric form. We don't deal with Cartesian vectors in physics very often. You will when you get to university, though. So anyway, work is basically just the energy that a force applied over a distance can put into an object. That's a simplified definition or example of what it can do. So for us in physics, in calculus, I'm going to say, well, let's say I've got a force that's equal to 2 comma 4, and I've got a displacement that's equal to 0 comma negative 3. What's the work done? Well, the work is actually just 2 times 0 plus 4 times negative 3, or a total of negative 12. And there's got a joules there as the example for that one. And so there it is. That's the work done. Okay. So let's actually take a look at what this actually means, right? Well, let's say I've got a displacement of 0, negative 3, all right? Here it is, 0, negative 3. Okay, maybe I'll make that in. So there's my displacement. Now I've got a force of 2 comma 4. So 1, 2, 4. So this is my force. This is my displacement. Basically what's happening here is I've got some kind of force that's pushing on an object like this while the object was moving like that. So how much energy did the force put into the object? Notice it's negative. Well, that means that it took energy away. And that makes sense because if you take a look at this picture, the object was moving downward, but the force was pushing upward. So we know that the overall result of this was that this force must have slowed down the object. And as a result, you have a negative work here. All right. So that one is kind of the idea for work. All right. And this is an example where I gave the vectors to us in Cartesian format. If you happen to get them in geometric format, you simply just plug in the values as seen here. Okay. The next thing is called the vector projections. Okay. And these are interesting because remember what I was mentioning actually before. So these vector projections in these examples or in these applications, what you're doing is you're actually projecting vectors onto other vectors in an attempt to kind of see how much of a vector goes in the direction of another vector. All right. In a way, this work example was similar to that, because what we've done here is we've sort of projected the force vector onto the displacement vector here, And as it turns out that this right here, it would be force cosine theta, all right? And it's going to be the vector that's responsible for slowing taking out this 12 joules of energy here. This purple vector is going to be doing that, all right? The rest of this force vector doesn't go towards slowing the object down, because remember, the object is moving straight down. All right. So vector projections. So let's go back to the concept here that I was talking about earlier. What's the geometric interpretation of a dot product? Remember what we did is we basically took one vector here, and we sort of, in a way, thought about how much of is this vector, in a way, going on top of the vector A. So how much of you imagine kind of like doing a shadow of a vector. Imagine I'm having like a flashlight up here, right? So your typical flashlight shining down, and then you've got you're projecting like a overhead projector in a way. You're sort of building a shadow of B onto A. And what you're able to do is you determine how much of B is actually in the direction of A. Why is that important? Well, because, in the case of work, for example, going back to this work example, whoa, there's kind of crazy thing happening there. Oh, we can recover. We can recover. We're going to work. We're going to work. There it is. Because in the case of work, what we needed to do is we needed to essentially sort of take a flashlight here and project, in a way, the light from this force vector down, and see how much of it is going in the direction of the displacement, so we can determine how much of this force is going towards slowing down the object, or speeding up, for example, as well, in a different scenario. Okay, so we'd end up having what are called vector projections. Okay, and there are several formulas for this, right? And they're found on the formula sheet. Okay, and we'll go ahead and write those guys down. Where do I have them? Here, somewhere in this area. Projections. Here they are. Okay. And so you would say the PROJ is the projection of a vector V onto another vector U, right? Is, let me go back to the regular, is equal to, right? In a way, you can look at it as the V magnitude cosine theta. Cosine theta times U vector over U magnitude. All right, and that's in the Cartesian format, geometric format. Or you can, if this is if you have the vectors in geometric format. Geometric format meaning you have a magnitude and an angle. And we got projection here as well. Projection. I can project a vector a vector V onto U, And if I have my vectors in Cartesian format, I'm going to do v dot u over u dot u, and take that whole thing and multiply it by vector u. Okay? And that's kind of the idea. Then there's another thing where is if I've got the magnitude, if I've got another vector, I want to project v onto u, but I only want the magnitude. I don't want to preserve the direction. Then it's simply just v magnitude cosine theta, right? Right. Projecting u onto v. And then over here, hold on a second, let me double check this. No, that's right, sorry. It's getting late over here, so that's correct. And in terms of if I want just the magnitude of the projection of v onto u, and my information is given in Cartesian format, it's simply just v dot u over u magnitude, okay, absolute value, right? And that's going to be the magnitude of the projection, all right? So let me just reiterate what this is. This is the projection of a vector, v onto u. If your vectors are given in geometric form, you use this formula. This is the magnitude of a vector. Sorry, this one is the projection of v onto u as well. And you use this formula if your vectors are given in Cartesian form. Here is the magnitude of a projection. You use this formula if your vectors are given to you in geometric form. This is the magnitude of the projection, and this is if your vectors are given in Cartesian form. Okay, and those are some of those questions there. Okay, do a couple of examples here just for completeness. Let's say I've got a is equal to 3, 4, and b is equal to 2, 5. C is equal to 3 at 17 degrees. Let's say these are in trig bearing. And D is equal to 4 at 100 degrees. What is the projection of C onto D? Oops. Let's go D. Well, I want to project C onto D, and so my vectors are in Cartesian form, geometric form. So I'm going to use this formula over here, this one. All right. So I'm going to go ahead and place my C vector where my V vector is. All right, you can kind of see that. My C vector is my V vector, and my U vector is my D vector. All right, this is supposed to be a D here. All right. So basically it starts out by magnitude of C. Well, magnitude of C is 3. Cosine of theta would just be the cosine of the angle between these two vectors, which would be 100 minus 17. Then it's the u vector, or actually, I guess in this case it would be the d vector, and divided by the magnitude of the d vector. Well, the d vector is 4 at 100 degrees, and the d magnitude of the d vector is 4. Okay? So, in the end, the projection of C onto D is 3 cosine of 100 minus 17. I don't know why I chose 17, because now I've got a funny angle of 87 here. So I need the cosine of 87. All right, so it's some tiny, times 3 is about 0.16. 0.16. This 4 and that 4 cancel, and I'm preserved as 100 degrees as my direction. All right, so the projection of C onto D is 0.6 at 100 degrees. And you might be thinking, okay, well, what the heck is that? Let's take a look at that. Let's first draw vector 3 at 17 degrees. So 1, 2, 3. That 17 degrees is like maybe there. All right. This is 3, and this is 17 degrees. All right. Then let's draw vector, the other one, which is 4 at 100 degrees. 100 degrees is like that, and 4 is there. This is vector D, and this is vector C down here. All right. Now I want to project this other one. I want to project C onto D. So basically what I'm doing is I'm sort of, in a way, putting a flashlight here, and I'm shining down onto D, and I get this really tiny vector of 0.16. And what direction is it? Well, it's at 100 degrees, because D is at 100 degrees. All right? And so when you project a vector C onto the vector D, the resulting projection is in the direction of D. So notice it maintained the direction of D. And then all of the rest of this stuff over here, all of this stuff in here, okay, produced the 0.16, which is sort of the amount of C that is projected onto D. All right? That's the vector projection. All right? Let's do the projection of B onto A. All right? So if I project B onto A, these are in Cartesian, so I'm going to use this formula here, where B is vector V and U is vector A. So I'll go ahead and write this out. So the projection of B onto A is just V, or B dot A. So B dot A over U, which would be A dot A, times the vector A. All right, well, what is this all going to be? Well, A dot B is a really simple thing, or B dot A, I guess. It's going to be 3 times 2 plus 4 times 5. A dot A is just 3 times 3 plus 4 times 4. And then A itself is simply just 3, 4. Okay? So basically it's like that is that, this is this, and this is that. Okay? Coming from this formula over here. And now if I just sort of calculate all that stuff out, this looks to be like I'm getting 26 over, is that right? 26 over, what's 9 times 16? 9 plus 16 is 24. And then I've got 3.4. 3 comma 4. And so, in a way, this is equal to, well, whatever 26 over 24 is. So it's like 1.02 or something times 3 comma 4, which is just going to be something like 3.0 whatever, 6 comma 4.04. Right? It just depends on whatever 26 over 24 is here. Oh, I was wrong about that. It's 1.08 here. That's an 8. And so that means times 3 is going to be 3.25. Sorry about that. That was a pretty bad guess. 25. And this one is going to be times 4. 4.3 repeating. This one here. 4.3 repeating. All right. Anyway, so there's our dot product there. Let's go ahead and draw the geometric interpretation of that. All right, so first of all, let's draw out those two vectors, A and B. All right, I'll put them on a coordinate plane here. We got 1, 2, 1, 2, 3, 4, 5. This is vector A. And then vector B, this is B, actually, 2, 5. Vector A is 3, 4, which would be this. Okay. And now, if I attempt to project B onto A, then I'm basically projecting down like this here. And I end up being a vector that's slightly longer than A. And if you were to draw this vector 3.25, comma 4.3, then that would be 1, 2, 3.25, 4.3, which is this green vector here. All right. And that's the projected vector of B onto vector A. Right? We got a vector that's almost the same as A, just a little bit longer. Okay? My diagram's not that great. Anyway, some vector projections. Tomorrow, next day or two, we'll talk about vectors in 3D.